Right now, let's introduce Mike Gamble. This is a man who needs no presentation. Mike has been here many times. So the differential CMG operation that Mike is going to present is a follow-up to his previous presentation, the history of Boeing CMGs, which was presented earlier at APEC. After presenting the history of Boeing CMGs at the COFE conference, Tom Valone actually encouraged Mike to build a small working demo model based on his past Boeing gyro work. So this presentation documents his initial year's research, fabrication, and testing of that first demo unit, and it is going to include his traditional in-depth mathematical system design and analysis. Mr. Gamble, welcome back. Let me hand things over to you, sir.
Okay, so we get the screen share running here. Do I open the file first and then go to screen share, or screen share first?
Oh, I would open the file first.
Okay.
Yep, and then go to screen share, and you can just put it on the file.
Okay.
It'll let you screen share the window that it's in.
Yeah. Okay, last time I tried slideshow and it didn't work, but we'll try it again.
And let me see.
Yeah,
It's going to the other monitor. Yeah. Yeah, you're still in your main window. You're still in your PowerPoint window. Your slideshow is probably on your other monitor.
Well, I don't have another monitor, but okay, it doesn't
2017.
Doesn't work, so we'll just stay right here then. We'll make this as big as possible. And we'll just go like that then.
There we go. Yeah, I think that works.
That works. Okay.
I will mute myself out, sir. And thank you once again. You are, I don't know what you call it. You're like a backbone of this conference, and you've done so much on inertial propulsion. So thank you. Thank you.
Yeah, this is more on inertial propulsion. Like you just got done saying, I pitched this at the coffee conference there, and Tom about went ballistic. He says, you got to build one. So I've been working on it.
Yeah.
This is first year's documentation of it. Anyway, we'll just keep going here from the, why aren't we changing? Something isn't working here. Let's try this. There we go. Okay. As we talked about earlier here, I presented from my Boeing work. Boeing did a lot of CMG inertial propulsion systems, which are on satellites as we speak, and also on the International Space Station. Anyway, Tom says, well, you got to build one of these things for me. So I said, okay. So problem is, me being an engineer, you're going to get a lot of numbers because that's what engineers love. How come we're not going here? There we go. The clicker's not going that good. This one's on differential or scissoring gyroscopes. It's one way of producing linear forces from rotary motion. There's other methods. We had a guy earlier that had another method. Dean drives is another one, rotating and counter-rotating masses besides gyroscopes also do the job. We'll start with this quick review here on polarization of rotary forces. If you want to call this the secret ingredient, I guess you could. This chart shows the basic process of polarizing a rotary force. If you're an electrical engineer like me or a tech, it's very similar to rectifying AC electricity into DC. On the left there, if you rotate a mass at a constant radius, all the forces are equal, so it just vibrates. However, going to the center chart and to the right-hand side, if you decrease the forces, does this pointer works? Oh, you're not there. I'll assume it works. if you decrease the forces on half the cycle and increase them on the other half the cycle, as the red arrows show, the average force moves from the 0 point off center. On the right-hand side here, you see the bottom portion of the curve is flattened and the top portion is accented, and therefore the force vector moves off the 0 point to be polarized. And there's many ways this can be done. It can be done by moving multiple masses. It can be done by changing the radius, the curvature. It can be done by torquing gyroscopes, which is the way we're going to discuss here. We'll start with some pictures of the test article here. This one has the gyroscopes mounted in the horizontal position, which is thrust in the forward direction. The front of the vehicle here has the servo controllers, which run the servos, which slew the gyros. You spin it around on the backside here, you have the instrumentation, power supplies that run the gyroscopes themselves. And then we will take a side view of it. This shows the gyros swing back and forth on both the left and side views of it. However, to take force measurements, I was using a load cell. So what I had to do was convert the thrust vectoring from horizontal to vertical. So we take pictures of that. Shows the gyros in the other position. Same frame and everything, only now the gyros are mounted vertically. And the side view shows it a little bit better. You see the gyroscopes now, they swing up and down rather than left and right as they were in the other picture. And that was so I could get good load cell readings. We'll discuss that a little bit more in detail here. First, we'll talk about inertia. When you deal with inertia propulsion systems, you have to calculate all the inertia of the systems so you know what you have and what you need. So we start rotational inertia I, and the radius of gyration K is the numbers we're interested in to make the thing go. There's two ways you can do these calculations. You can use the textbook equations for mass and radius, or you can use a cheat sheet, a lookup table based on area. For this operation here, I use both methods, starting with the mass radius one. From the textbook equations, inertia is equal to the mass times the radius squared. In this case, the test article weighs 17 pounds and the center of gravity is 1.776 inches above the base plate. And then from the base plate down is your D dimension of where you want the torque to rotate on. And then if you plug in all the numbers, you come up with converting the 17 pounds into kilograms, you get 7.711. And then you take your offset distance plus the distance D, you square those. Then you divide by 39.37 squared, which converts inches to metric. You come up with kilogram meter squared. Now going the other way, uses lookup tables for rectangular plates, and it calculates the rotational inertia from the center point and then a distance D to an offset or translated point. And the way this one works is you take the mass times the height times the width squared of the plate divided by 12 and then square the offset distance. And then you got to throw some conversion constants to get to kilograms and meters. So taking a look at the system plates, this is what you have to work with. Now the base plate is 12 inches by 3.75 inches thick. center line on that one is the D distance that you're trying to go to, where your rotational point is. And then the 6x8 plate is above that. Its center line is here, which is 3.188 inches above the base plate. The top plate is 1.5 inches by 0.313, and it sets 6.34 inches above the base plate. Now, the number that you want is from the gyro center line to that point of rotation, which is called the radius of gyration, or the K factor. That's the number you're trying to get. And to do it, you have to plug in a whole bunch of numbers and do a bunch of algebra, which gets very time consuming. So we're going to go through this very quickly. The bottom plate weighs 5.165 kilograms. It's 12 inches by 0.375. You square those, divide by 12, square your offset distance, convert to inches to meters. And then you go to the front plate. It weighs 0.398 kilograms. It's 6x8 inches. Square those two, divide by 12. It sits up there with an offset 3.188 inches. You square that term, convert to meters. Rear plate, same dimensions, only this one weighs about twice as much because it carries the instrumentation package. So you square those, the 8 and the 6, and it has the same offset distance. And then you convert to meters. Now the gyros, the two gyros weigh 1.164 kilograms. There is 3.688 inches above the base plate plus the D factor. You square that term, convert to meters. Top plate, 0.19 kilograms. It's 1.5 inches by 0.313. Square those, divide by 12, and it sets up there with an offset 6.344 inches. When you get done doing all the dirty mathematics there and you combine everything, add it up, take out the constant factors, you come down here, you get 7.711 kilograms. D squared plus 2.412D plus 13.995 divided by 39.37 squared. And that takes everything over to kilogram meter squared. It's a long drawn out process. Oh, come on, let's go to the next page here. How come we're not going? There we go. Okay, next page here is you take the calculated from the mass area from this chart and the mass from the previous chart, set them equal. By inspection, the kilograms go out and the 39.37 squared goes out. So what's in parentheses, you set equal to each other. D squares go out, so you move the D's to one side and the constants to the other. And you calculate D to be 9.475 inches. K is add 3.66 or 688. And the number that you're looking for is 13.163 inches, which is your radius of gyration. And that will be used in compute. Well, this thing just wants to keep going down and not shift. There we go. Okay, now we have to do all the inertia calculations for all the individual parts, starting with the gyroscopes. And that's done by taking the manufacturer spec. These little gyros, they're about a 2-inch wheel on them. And they spin at 16,000 RPMs. It weighs 145 grams. And then you got the inner and outer frame diameters and the mass of the frame, inner and outer diameter of the rotor and its width and its mass. And then you, next step is you plug those into all your inertia equations, starting with rotational inertia, which is mass times radius squared. So you have the inner radius squared plus the outer radius. And then you got to convert from grams to kilograms and from millimeters to meters. And when you get all done, you come up with 6.3206 e to the minus 5 kilogram meter squared for the rotational inertia of the rotor. And then you need the angular momentum, which is times omega. And now omega comes up to be 2 pi times 16,000 revolutions divided by 60 to get frequency. And you multiply that and you get 1.059 e to the minus 1 kilogram meter squares per second for angular momentum. And then we move on to kinetic energy, which is I times omega squared divided by 2. So you take your inertia calculation there, you square up omega and you get 88.5159 joules for energy. Torque now is equal to power divided by frequency. So power is equal to the input power. In this case, it's 6 volts times a half amp or 3 watts divided by omega, which is the 16,000 converted to frequency. And you get 1.6114 e to the minus 3 Newton meters on torque. And then we wind up last over here. You have acceleration, which is torque divided by the inertia. So we just calculated the torque and we already have the inertia. So when you divide those two, you get 25.4951 radians per second squared. Now those are the numbers for the gyroscope rotor. That's your source generator. Now we have to go to the frame and do basically the same thing. So we start with the picture of it here. We're going to now take the inertia of the motor, which is offset the radius of the gyroscope, and then the gyroscope frame, which is 2 rings. The motor is 58.2 millimeters long and 28 millimeters in diameter, weighs 56.7 grams, spins at 16,000, consumes 12 volts, 2.5 amps to start, half amp to run, which is 15 watts starting and 3 watts running. And then we pretty much run through the same set of equations, only this one's a little more complicated. To calculate the inertia, you have to do a hoop in the vertical direction and then a hoop in the radial direction. And then you have to translate the inertia of the motor. So we do this in basically 3 sections. The first part is the hoop in the vertical. Second one is the hoop in the radial. Then the third one is the motor, which is calculated as a cylinder, which is translated to the frame diameter. And so we start with the 2 hoops. It's mr squared divided by 2 for the vertical hoop and mr squared for the radial hoop. When you add those together, you get 1.5 times the mass times radius squared. If you use the averaging, it's inner radius squared, outer radius squared divided by 2. Plug in all the numbers, you get 4.637 e to the minus 5 kilogram meter squared for the 2 hoops, the frame of the gyroscope. And then the next chart here, we will do the motor. First, we calculate the inertia of the motor on the first one, which is mr, the radius of the motor squared divided by 4 times the mass of the motor times the length of the motor squared by 12. When you work that number down, you get 1.8803 e to the minus 5 kilogram meter squared. And then you have to translate the motor's inertia by an offset distance equal to the radius of the frame. So when you work that part down, you get 2.2587 e to the minus 6. You add that to the motor inertia, and you get, for a total, you get 2.1062 kilogram meter squared. So then the next step is to put it all together. You take the 2 hoop equations, and the motors have to double the translated one. So you multiply it by 2, take the two hoop ones, add them up, and you get 8.8494 e to the minus 5 kilogram meter squared. So that handles the motor inertia and the frame inertia. And we have one more, which is the servo. A lot of inertia numbers when you're playing with inertia systems. So this next one here, you have a servo that rotates it, and it generates 57 ounce-inches of torque. Now, mechanically, it will rotate plus or minus 90 degrees. However, the electrical servo or the software, the controller that runs it is limited to plus or minus 45, so there's some limitations there. Speed is 60 degrees, 0.19 seconds. It weighs 37 grams. 6 volts at 1 amp for 6 watts of power. So then we go down, we pretty much run the same set of numbers one more time. First one is rotational speed. You take your 60 degrees divided by 0.19 seconds, convert that to radians, and you get 5.5116 radians per second. And then you go for angular momentum, which is the inertia times the omega, and the inertia is 8.849. That was already calculated. Then we times it by the 5.516 omega, and you get 4.8775 e to the minus 4 kilogram meter squared per second. And you just go through the next set here, which is energy, kinetic energy now, which is omega squared. And that's 1.344 e to the minus 3 joules. That's a far cry from the 88 joules you got off the rotor. So this is a very low power system here. And watt-wise or power-wise, it's the same thing. You convert the torque times the frequency, and you get 2.216 watts compared to the 88 joules you got off the rotor. And the last one, again, is acceleration, which is torque divided by the rotational inertia. So you take your 4,100 gram centimeters, convert that to kilogram meters, and divide by the inertia, and you come up with 4.544 e to the 3 radians per second squared. That's pretty much all for the inertia calculations. Now we'll talk about gyroscopes, differential gyros in particular. And this is basics on gyros. There's 3 orthogonal or 90-degree vectors. The first vector is the spin vector, that's highlighted in red. And then the second vector is your torquer vector, that's highlighted in green. And the output vector is highlighted in blue. Now, when you operate them differentially, or in what is commonly known as scissoring, you spin them in the same direction. Spin vector is the same for both of them. However, the torquer vectors are opposite. One is clockwise, one is counterclockwise, and therefore you get 2 output vectors which are differential. One is clockwise and one is counterclockwise, or opposing torques. And then we'll run the numbers on that. The equation is the torque output of a gyroscope is the speed of the servo times the angular momentum of the rotor, which is the inertia times the speed of the rotor. And then I just color coded them here to match the vectors there. So the torque output's in blue. This is peak torque, and your servo speed is 5.516, and your rotor inertia, which we previously calculated, is 6.32 e to the minus 5, and the speed is 16,000 revs divided by 60 for hertz times 2 pi to get omega. And the output comes out to be 0.5837 Newton meters, or 0.4305 foot-pounds, or 82.657 ounce-inches. That's the peak for each gyro. Now we'll talk a little bit more on the differential torques and what those do for us. Starting with the basics of torque definition, you have a lever arm that's foot long, and you put 1 pound on it to get 1 foot-pound of torque, which is equal to 192 ounce-inches or 1.36 Newton meters. Now, where it gets a little interesting here, when you take most physics problems, the lever arm is assumed to be massless. Well, that doesn't work in real world engineering. You have to account for the mass of the lever arm. So the next step is we start with the calculation of the inertia of the lever arm, which is the width times the length cubed over 3. So it's a 1/2 inch thick, 12 inches long. And then you got to convert that to metric. So you wind up with 1.195 e to the -4 kilogram meter squared. When you take the torque and the inertia to get acceleration, you get 11.38 e to the 3 radians per second squared. What actually happens after you get rid of the math is the mass of the lever arm delays the acceleration or the application of the torque, because you have to accelerate the mass of the lever arm. So it's kind of a delayed response. And here again, you have orthogonal vectors. Your force vector and your torque vector are 90 degrees apart. Moving on to the differential diagrams for torquing, we start with a free body diagram, which you have the 2 torques counter-rotating, separated by a distance lever arm of distance d. Now, if those 2 torques were applied on a concentric shaft, nothing would happen because the torques would just cancel each other. Torque 1 equals torque 2, but they're in opposite directions. Well, when you put a lever arm between them, it gives them something to work with. So we do the number crunching on that. Now, me being an electrical engineer, I kind of solve the problems backwards. However, I think you get a better understanding of what happening. So I take the torque here and I draw a lever arm on it. I put a force vector on it at 90 degrees for both torques. And then when you split the lever arm in half, and in the center point down here, that's your radius of gyration K. That's the number that we calculated off the frame inertia. And what you're left with is a couple of triangles. You have the big triangle here, which is half the separation distance, radius of gyration plus the radius on a one triangle. And when you get down here, you have the force vector split into the X and Y components. So by trigonometry and congruent triangles, you can come up with the cosine of the angle is equal to the big triangle and the little triangle. And then you set those two equal, you can get the radius and the radius of gyration. Now, like I said before, I do the calculations backwards because, for me, it's the correct way, but if I was a mechanical engineer, they'd do it the opposite way. That's why I call it a reverse solution. When you plug in the numbers, now you go back to the K calculation from the inertias, you get 13.163. You plug that into the theta angle, and you get 2 times the 13 divided by the separation distance, you get 80.3 degrees. And the radius is the sine of that. So you take the 13.13 divided by the sine of 80, you get 13.35. You plug that into your torque equation, which is the d, which is the separation distance, times the torque divided by the radius. And so you have the torque, which is the 0.43 foot-pounds, times the separation distance, and then you got to convert to feet, and there's 2 gyros, so you multiply by 2, divide by the radius, which is in inches, and convert that to feet, and you come up with 0.404 pounds peak, calculated output force of the 2 gyro system. Now, this chart would be what I would call the normal solution. This is the way a mechanical engineer would solve the problem. You take your radius of gyration down to the point of rotation, and then you draw your radius vectors in, and your force vectors now set up where the torques are. To me, that's not intuitive, because when their force vectors are down here, you can actually see what's happening. Here you don't, but you can picture it that the force vector here to the left and to the right would cancel, and the two force vectors in the y direction would add, but it's not quite as intuitive. That's why I sort of work them backwards. Now the next one is I do a little bit of testing on this angle. The smaller the angle, the more force the system generates. So you have two variables to work with, the separation distance d and the radius of gyration k. So the first entry was what we just calculated. Now, if you separate the gyros a little bit more, say add 1 more inch, now you start decreasing that angle. If you could get the radius of gyration, which is based on mass, down to say 5 inches, you can reduce that angle a whole lot more. Yeah, so that's work in progress as far as improving it. Now, this equation simplifies or is more complete because it shows all the individual parts. You have I lumped all the constants together up front, and you have the speed of the servo times this, oops, pushed the wrong button, times the speed of the gyros, times the mass of the gyros, times the dimensions of the gyros, times the separation distance over the K factor squared times 4. So you plug in the numbers, the speed of the gyros is the servos is 0.877 hertz. The gyros spin at 266.67 hertz. Mass of the rotor is 112 grams. The inner diameter is 41.3. Outer diameter is 53.0. Separation distance 4.5, and the radius of gyration is 13.16. And of course, you get the same number, 0.404. However, you can see what parts contribute. Well, in looking at that, by changing the separation distance and the radius of gyration, you increase the separation distance and decrease the radius of gyration, you can improve your numbers here. Now, the numbers in red are the minimums that are required for movement. And we'll get into that a little bit more. You also have a slight option of increasing the servo speed here. Everything else here is fixed by whatever gyros you have. In this case, this is a 2-inch gyro, so all those numbers are constant. The next step is we'll look at the instrumentation electronics and dig down into the schematics a little bit. The electronics on this thing, they're powered off the same 6-volt supply that runs the gyro motors, and they're designed to monitor both motor voltages from 0 to 6 volt scaling, both motor currents 0 to 3 amps, both motor frequencies 0 to 300 hertz, and then it also monitors the load cell 0 to 10 pounds. And then all that goes out to a connector. You can connect up to an oscilloscope so you can monitor all your perimeters. The schematics of the thing, you get your 6 volts in here. Power switch goes up, turns the 2 gyros on. Also runs in here to a DC to DC converter, which powers up the plus and minus 12 volts that runs electronics. And then we grind the plus 12 volts down to 5. For a run, the load cell only takes 5 volts. Well, then you get up here, you have a monitor the voltage from the motor. You monitor through a current sense resistor from the motor, and then you have a infrared pulse counter that monitors the speed of each gyro. Goes down to a selector switch so you can monitor left or right gyro. And then the outputs are all buffered, isolated, and scaled. You got the voltage scaling, the current scaling, and the frequency scaling. And then the load cell is scaled over here. And they all run out to VCN or coax connectors over here that go for the scope monitoring. Now the servo is a little bit simpler. It's a little single chip controller. You have to program it for a sawtooth, so it goes fast in one direction and slow in the other. It's powered by a second power supply, separate 6-volt power supply. It does have a few problems. It only drives plus or minus 45 degrees, so you don't use the full range of the servos. And it uses the same time base for the power stroke and the reset stroke, which causes some problems. We'll get into that right quick like here. Next chart here. The servos swing from a minus 45 degrees to a plus 45 degrees in 100 milliseconds. However, on the reset, which takes 600 milliseconds, it goes in 100 millisecond steps. So it's not smooth, it's jerky a little bit. So the total rep rate is 700 milliseconds for each stroke. And then we'll go over here to the force measurements. This was the reason I had to change the from horizontal to vertical. I use a what's called a load cell, which measures compression load, and it converts that to an electrical signal. The scaling is 10 pounds maximum, so the scaling is 1.5 pounds equals 1 volt. The problem is it only measures in a compression mode, so any force in the X direction wouldn't apply. So what I did is I changed the gyros for vertical thrust, and then I put the load cell under the lip of the test article. And so as it generates some vibration, I dampen that out because I'm looking for ounce force resolution. So I have to dampen out some of the vibration by the weight of the vehicle. Now the weight, 17 pounds, it's about a 40-60 distribution. So there's 6.7 pounds DC preload on the load cell. And then there's a scale factor. The gyros are setting 5.5 inches from the fulcrum, which is the rear wheels, and the load cell is 15.5 inches from the fulcrum. So there's a gain of 2.818 on the measured data. So when you do the data reduction to get the force generated, you have to subtract out the DC offset of 6.7 pounds and divide by the gain factor of 2.818 to get the real numbers of the force being generated. Now we get to the fun part of actually firing it up and measuring the data. Okay, the first scope plot is on the motor speed, voltage, and frequency. Okay, the yellow here is the voltage applied to the motors, which averages out to be 5.72 volts. The purple down here is got a little more ripple to it. That averages out to be 0.55 amps. So multiply it together, you get 3.15 watts of power. Your square wave here, the period on that square wave is 3.75 milliseconds, which translates to 16,000 RPM. So I can verify that both gyros are up to speed and running per manufacturer spec. And the next thing I did was a noise measurement. I ran the servos back and forth on their sawtooth pattern, but I didn't fire up the gyroscopes. They're just a dead mass, and I'm looking for the background noise, and this is what it comes up to be. So their system is noisy. Now the next step is I did just the opposite. I turned off the servos and I turned on the gyros, and the noise spectrum is about the same, only it's a little more ragged. So there's quite a bit of noise to deal with. Now this one is the actual data here that we took. You can see the pulse coming up, power pulse coming down, and then there's this plateau on reset There's your 6 pulses because it's not smooth, and the rep rate is 700 milliseconds. And if you look at the number here, you're up to about 0.43 pounds peak force being generated. Now we'll do a little analysis on that. And then going back to the simulated servo plot, we now put on the force. So in the 100 milliseconds, it goes up to 0.43, and then 150 milliseconds, it comes back down. However, you get, because of the stepped reset, you get a slight DC offset here. When you take the average, it averages out to 0.128 pounds. And the torque rates, you got 15.708 radians per second for the high-speed power pulse, and you get a minus 2.618 radians per second for the reset. Now that's not smooth, so that's a little bit of a problem there. Now the averaging equation is basically half the peak value times the square root of the duty cycle. So the peak goes up 100 milliseconds up, 150 milliseconds down with a rep rate of 700 milliseconds, peaks out at 0.43. So you take that in there, divide by 2, and then you take the, add your peak pulse divided by the rep rate, take the square root, and you get the 0.128 pounds, which is 2.05 ounces. However, to make this thing move, it's going to take 3 ounces of average force. Now then, I did one off-axis noise test. I measured in the vertical axis, but I turned the gyros around and had them swinging in the horizontal or forward direction and measured the off-axis vibrations. And you see that's even worse than the on-axis vibration. So the system generates a lot of vibration because you're torquing gyros. That causes a problem. Now I'm going to try and run a little clip here. I don't know how it's going to work, but we'll give it a shot. If it'll come up, let's try that. There we go. And no, it doesn't want to start. I don't know how to do that. No. Looks like we're,
you know, Mike, are you showing your so I don't know which window you have, but if you have,
I only got one window, so what it's doing.
no, I mean your virtual window. I mean, if you highlighted PowerPoint, because it's not even showing the clip. It's not showing the window.
Well, I know it's not running either, and my screen went dead.
Oh, okay.
It did something crazy.
Yeah, I wondered if maybe you displayed your
Hang
power.
on a minute, I'm going to try something else here and see if we can.
Okay, yeah, no worries, no worries.
Does that show up?
Now you got it. Yes, sir.
Yeah, no, the trick is to try and make it run, and it's not doing that either. I can't.
It could be. You know what? Down there in the center, that play button, is that doing it? Your mouse is lagging. I think maybe you got too much running.
Well, that could be. I don't see a play button though. That's the problem.
Okay, in the dead center, you see the 10 on the left and the 30. Dead center on your screen on the very bottom. Your mouse is right near it. Nope. There you go.
Right there?
Yeah, you get a little play button. Dead center. You get
I don't see it, but I'll click on it.
Nope, that's your seek button. That's your seek button. It's below your toolbar. You got a little 10 and a 30, right? On the left and right. I'm hoping you see.
We just lost everything here. I don't see a 10 and a 30. I'm not knowing what you're looking at here.
Right down at the very bottom, dead center. You should, I'm hoping, you should have a.
Well, it says chat 99 plus if I'm.
No, maybe you're seeing a different view than
I'm seeing something else. We're not seeing the same thing. Unless I got to go back over to the, oh, wait a minute. Here we go. Let's try that. Ah, there we go.
Okay, good deal, sir.
Yeah. Now, I don't know if I can get back to where I wanted to be, but we'll try that next. Okay, new share. Let's see. I think this is the one we want. Okay, we're back on PowerPoint now. Oh, what are you seeing now?
Yeah, sorry, I was muted. Yep,
Oh.
you are back on PowerPoint.
Okay,
You're
we're
good
back
to go.
on PowerPoint. Okay, then we'll do the conclusions here. The demo unit and its documentation showed that the differential or signal scissoring gyros will produce linear forces. And that force that's generated is a product of three terms. One is the size of the gyros, which is rotor speed and mass, and the speed of the servos. And then you have the inertia of the frame, which is the radius of gyration and the separation distances. So those are some of the variables you have to work with. And then three there, I changed the gyro orientation to vertical so I could run a load cell and get respectable numbers. However, number four there, the generated output force was only about 75% of what's required for movement. So it did not move, but we definitely got in the ballpark. So the next chart here is on improvements that need to be done to get it to move. Optimization, we need a better controller to get a smoother servo rate to separate the power and the reset strokes. And we need to change the test article, increase the gyro separation, and then decrease the radius of gyration by lightening the frame. And also more powerful or bigger mass gyros would work. Now, this detailed analysis that we just went through is also valid for the Boeing CMGs here that I showed in the previous presentation. If you remember this picture from the history of Boeing CMGs, this was old bug eyes that we played with. It's that big, 4 big gyros. Those are 24-inch wheels on there. There's 2 on the front and the 2 on the back. You can't see very well, but it generated hundreds of pounds of force. And then the gyros are also gimbaled for thrust vectoring. And that was the little play toy we had in the lab there. And if anybody's interested in finding out more about gyroscopes, this is the website I recommend. It's the one that I use, gyroscopes.org and gyroscopes.com. And then we'll wind it up here. And hopefully I haven't bored you with too many numbers because it was a long, detailed analysis. And if you're still awake, thank you. And any questions?
Good deal. Okay, so let's do this. Mr. Gamble, let me stop your screen sharing. I want to.
I was just looking for the button.
Yeah, I want to put this on gallery view. Everyone, giant applause for Mike Gamble. Mike, thank you so much. Thank you so much. And I know you have more to share, and you are always welcome to come back and share. You have,
whenever, like I said, I can do one a month. I have 5 of them on getting this thing running. It does run, but this was the first year, the initial cut. Like I said, Tom twisted my arm to build it, and this was throw it together and see what you get, and then you go optimize from there.
yeah. Well, you've got a wealth of information, a wealth. I mean, a career's worth of information, right? But then, especially when it comes to inertial propulsion and working at Boeing and the gyros and all of that, you have this unique experience and knowledge that you've applied so well. So thank you again.
I'm happy to pass it on to anybody that's interested.
Yeah.